Hello, welcome back to our course Advanced Quantum Mechanics. This is lecture 20. Remember, we started with describing a system, a quantum system, through its Hamiltonian, and then we used the Poisson brackets or the Heisenberg commutation, the Heisenberg equations of motion to obtain then the operator valued functions of time obeying the canonical commutation relations and the hermiticity conditions and the equations of motion. And then we introduced a initial state vector psi in order to boil this down to number value predictions as a function of time. And we spent quite a bit of time on both the first step and here this second step. This was all about representation theory here. Now, let us focus on the dynamics. You see, we've studied the framework so far in quite some detail. Now let's look at the dynamics. And especially on the question of how can we do this efficiently? See, there's an issue of complexity. Imagine we have a system that has many different particles in it. So, okay, assume that our Hamiltonian has many variables in it. So it's an x hat 1, x hat 2 of the first particle, x hat 3 of the first particle, and then there would be the momenta x1 of the first particle and the momentum 2 of the second particle, of the first particle, and then all these guys have hats. And then for the second particle, again, 6 different canonical observables. So we would have the x1 direction operator for the second particle, and then x hat for the second particle too, etc. So there could be plenty of those, and eventually we have, let's say, the momentum operator of the nth particle in the third direction. So lots of operator valued functions of time if we have plenty of particles in our system. But that means that we need to find these as functions of time. So need, e.g., x hat for the fifth particle, second direction, function of time, etc. Plenty of them. There are how many of those? Well, 6n of those. Why? Because every particle has 3 positions and 3 momenta. So 6 different observables. And when we have n particles, then we have 6n of these operator valued functions of time to find. This can get really tedious. Remember that in this course we did it for 1 position operator, for 1 momentum operator, and that got plenty complicated. Now, fortunately, there is a way to solve for the dynamics of all of those operators by solving for just 1 operator valued function of time. So here's a very efficient way. Efficient method for calculating the dynamics. Namely, it suffices to solve only 1 equation of motion. Equation of motion. We will usually write EOM for equation of motion. And what is that equation of motion? Now here's the proposition. Assume that we can calculate a function u hat of t, which will be an operator-valued function of time that obeys the following equation of motion, namely I h bar d by dt of u hat of t equal to u hat of t h hat of t. And initial condition u hat of t naught being the time when we start the experiment, is supposed to be the identity operator. So assume that we can calculate such an operator-valued function of time, just one of those. If we can calculate it, we can solve this single equation of motion, then we obtain that f hat of t is equal to u hat dagger of t, f hat of t naught, u hat of t, for all t larger or equal to t naught, if f hat is a polynomial in the x hat and p hat operators with constant coefficients. What do we mean by constant coefficients? So for example, e.g., f hat of t being defined as the cosine of some alpha times t times x hat of t minus 7 p hat of t does not qualify. Does not qualify for our proposition because this coefficient here is not constant in time. You see, it's a polynomial in x and p, all right? If you like, let's put a third power here just to indicate that this really is a polynomial, but this coefficient is time dependent. And that's a time dependence that has nothing to do with the Hamiltonian. It's just that we chose an observable which has a human-made time dependence in it. The time evolution operator cannot, this thing will be called the u hat of t, will be called the time evolution operator. This thing, of course, cannot know what choices we make. So let me just write up what the name of it is. This is the time evolution operator. Okay, so we are excluding the situation that f hat is a polynomial in x and p that has time-dependent coefficients. But the most important observables usually are the x and the p anyway. So let us look at what qualifies, e.g. f hat of t equal to x hat of t of the third particle, the second component qualifies, right? Because its coefficient is 1, and that's a constant. So the claim here, the claim of this proposition is that if only we can solve this differential equation to obtain a time evolution operator u hat of t. Then, for all observables in which we haven't artificially built in some extra time evolution, so for all normal observables, we have that their time evolution is given by this expression. You take the observable at the initial time when you start the experiment, and you obtain the observable at a later time by applying the time evolution operator, the thing that solves this differential equation here, this equation of motion, by the left and to the right. Here you had dagger, and on the right you had. So in particular, the claim here is, of course, that this f hat of t obeys the equations of motion, and that f hat of t is Hermitian, if it starts out Hermitian, and that all of those f hat of t obey the right commutation relations as long as they obeyed them at the initial time. Let's check one of those claims. So in particular, does the equation of motion hold? So let's see. What we have to show, what we have to test is this, is IH bar d by dt of x hat of t, so I'm writing here EG, is this equal to the commutator between x hat of t and h hat of t? I might as well write down f hat or p hat of t. Doesn't matter. So let's just, to be explicit, let's write the x hat, for example. So let's check whether this is actually true for all times if we define, as the proposition says we should, if we define the time evolved operator to be related to the initial time operator through multiplying the u hat and u hat dagger from the right and from the left. So we check. So I h bar d by dt of x hat of t is, by the definition of above, it is IH bar d by dt of, well, x hat of t is claimed by the proposition, x hat of t is claimed to be u dagger x hat of t naught, u dagger, u hat of t. So let's try this out. We put here a u hat dagger of t, and then this is the position operator at the initial time, and then u hat of t. So this then is, by the product rule, because this thing is dependent on time and that is dependent on time, this is a constant, we have that this is u hat dagger dot of t x hat of t naught u hat of t plus u hat dagger of t x hat of t naught u hat dot of t. If you're uncomfortable applying the product rule to operators that depend on time, well, just insert resolutions of the identity, end up with matrices, and then products of matrix elements, which are just number-valued functions. And then you can use the fact that the product rule applies to number-valued functions. So it certainly also applies to these operator-valued functions. Now, at this point, we need to use the assumptions that go into the proposition, namely that by assumption, our u hat of t is the solution to this differential equation, to this equation of motion, namely that IH bar times the time derivative is UH. Okay, so at this point, we now use we use that IH bar U hat dot of t is equal to U hat of t H hat of t. Right? This is by assumption that the U hat of t is the solution to this equation of motion. And if we take the Hermitian conjugate of that equation, we obtain and minus IH bar, and then we have U hat dagger dot of t equal to, and then we have H hat of t and U hat dagger of t. In principle, we would need to put a dagger here as well, but remember that the Hamiltonians have to be self-adjoint, so we don't have to put a dagger here. But also remember that we took here the Hermitian conjugate of this product. And the Hermitian conjugation always flips the order of matrices. That's why the H ends up on the left and the U ends up on the right here. Okay, so we have this. And from that, we now obtain, this is equal to minus H hat of t, U hat dagger of t, X hat of t naught, U hat of t, plus U hat dagger of t, X hat of t naught, U hat of t, H hat of t. Right, so we used this here, and we used this over there. All right, but now we recognize that this, of course, is x of t, x hat of t, and this is x hat of t. And so therefore, what we obtain is that IH bar d by dt, just carrying this forward from above, x hat of t, is indeed equal to, well, x, h minus hx. So it's the commutator of x of t, h hat of t, which is what needed to be shown. So here we've shown that the position operator obeys the correct equations of that the position operator expressed in this way in terms of the time evolution operator will obey the correct equations of motion. And similarly, one can show that it also obeys the correct hermiticity conditions at all times and correct commutation relations. And it can be done not only for x hat, but also for f hat, for any arbitrary observable. From this, it's clear that the time evolution operator is a pretty powerful thing. It describes the dynamics of the system entirely. But more than that, remember, H hat describes everything about a quantum system. Quantum system, system. Now, U hat of, let's write H hat of t, U hat of t does too. Remember, the overall Hamilton principle was based on the idea that the energy expression of a given system, so the way that the energy is expressed in terms of kinetic energies and potential energies and the coupling energies between various subsystems, the energy expression contains all the information about the system, classically and quantum mechanically. And now this operator U hat of t, the time evolution operator, comes along, and it seems to be so powerful because it describes the evolution of all observables. It turns out the time evolution operator is exactly as powerful as h hat is, because from h hat of t, we can calculate u hat of t, but knowing u hat of t, we can also reconstruct what h hat of t is. So the claim is, in fact, knowing u hat of t, one can reconstruct not x hat, h hat of t. We can reconstruct h hat of t, which means that u hat of t knows everything about the system. It knows as much as the Hamiltonian does. And how do we see that? To see this, we notice that the equation of motion obeyed by our time evolution operator, this is the equation of motion obeyed by the time evolution operator, it implies by multiplying with the inverse operator from the left, we get rid of the u hat of t here entirely, and we just have it over there. And we can simply solve that equation for the Hamiltonian. So we obtain that IH bar u hat inverse of t d by dt u hat of t equal to h hat of t. So what we have here is that given the time evolution operator, we can calculate what the Hamiltonian is. In fact, this is comparatively easy. It's actually a little bit harder to solve the differential equation for u of t from h of t. But this is, of course, usually the way it goes. Let me just make a comment here. Comment. Feynman's formulation of quantum mechanics aims to, has quantum mechanics is built on u hat of t. Let's just write it like this. Is built on u hat of t. You never need to even know what the Hamiltonian is in principle. You can still calculate everything in quantum mechanics for this exact reason. On one hand, knowing the Hamiltonian, you can calculate the unitary time evolution operator h, u, by solving a differential equation, the one that we had above. And vice versa, once you have u of t, you can also calculate what the Hamiltonian was by using this equation in a box here. So they're equally powerful, and Feynman is focusing on this formulation here. Now, let us come back to the question of how to calculate u hat of t from h of t. So, practically, we will later in this course get back to Feynman's formulation, but for now, let's work within the framework that we have developed. So practically, how to calculate u hat of t from h hat of t. Well, we need to solve what we said we would need to solve above, IH bar d by dt of u hat of t equal to u hat of t h hat of t. and u hat of t naught equal to the identity. These are the equations that we need to solve. How can we do this? Well, there is a simple case and then there is a more complicated case. Let's do the simple case first. Case 1. And case 1 is that h hat is constant. This is a system that is entirely isolated. So we have dh hat by dt equal to 0. No interference from the outside. In this case, things are easy, because then we can immediately write down what u hat of t is. Namely, u hat of t is then equal to e to the power of 1 over ih bar t minus t naught h hat. Let's check. Well, first of all, you may wonder, what did just happen? We exponentiated an observable. We exponentiated an operator. What does that mean? How is that supposed to be done? Well, let's remember how we exponentiate a number. We don't exponentiate the number by plugging it into a machine. How do you actually exponentiate a number? Or how does the machine do it? Well, let's recall. Oh, let me just put here this. How defined? What's the exponential of an operator? Well, let's remember that if we're dealing with just numbers, so we start with a simple case where e to the power of lambda a, for example, is to be calculated. How do we do that if we don't have a machine available? Well, then we go back to the definition of what the exponential is, namely through a power series. It's just a Taylor expansion of the exponential, if you like. So this then is lambda to the power n, a to the power n divided by n factorial. And here we are claiming that the time evolution operator is this thing. And what we have here is numbers, all right, but the h hat is an operator. And here, we can think of lambda as being a number, and a, for example, being a number, or as we will soon see, we can also choose this to be an operator. But what we can see from this here is that we will need to differentiate that. We will need to differentiate u hat of t in order to check that it obeys the equation of motion. So how does differentiation of an operator, of an exponentiated operator expression work? Well, let's remember how this works for number valued things. It's all very straightforward. We have d by d lambda of e lambda a, and we can write this as the sum n equal 1 to infinity of, well, we are differentiating now in here. And as we do that, we obtain n times lambda to the power n minus 1, and everything else stays the same, of course. And we can write this in the following way. This is the sum n equal 1 to infinity, and then this n cancels one factor in the factorial here, so we obtain n minus 1 factorial here. We also have a lambda to the power n minus 1, and we have an a to the power n minus 1 if we pull one of the a factors in front. All right, so we then obtain that this is a times. Oh, by the way, why is this? Why did the term n equals 0 go away? Well, because the n equals 0 term was the term with lambda to the power 0, which is 1. So it was a constant term. And when we differentiate with respect to lambda, the constant term goes away. So the n equal 0 term went away. So what we have here is that this is the sum over m equals 0 to infinity. Simply, if we rename the m to be n minus 1, then we obtain that this is lambda to the power m. I'm sure you've seen this stuff before many times. But the point I want to make here is that, okay, so this is equal to a e to the power of lambda a, right, as expected. You all know that. The point I wanted to make with this is that a is here a mere spectator. At no point in this calculation did we require that a is a number. It might as well be a matrix or an operator. The only thing that we required here is that we can take powers of it. And that's what we do here with the Hamiltonian. The Hamiltonian is dragged along just like this a, right? So this expression is meant to be viewed as a power series. It's a shorthand notation for the power series, as is every exponential, by the way. And we also just convinced ourselves that differentiation will work as usual until it won't. But for now, it does work as usual. And what does that mean? So, so what we have is that u hat of t, which is, remember, 1 over ih bar, t minus t naught, etc. It's e to the power of 1 over ih bar, t minus t naught, h hat, is actually the sum n equal to 0 to infinity, and then 1 over ih bar to the power n, and then t minus t naught to the power n, and then h hat to the power n, 1 over n factorial. Then we obtain that ih bar d by dt, this is something we can conclude, of u hat of t is equal to, well, we could go through these steps again, but we have convinced ourselves that it doesn't matter that h hat is an operator here. So we might as well just look at what this is and differentiate that with respect to t. And we obtain that we get a prefactor of 1 over ih bar. So we have ih bar divided by ih bar. And the t derivative is just giving us a 1. And then we also have this h bar here, this h hat here, and then multiplied with this whole thing again, because it's an exponential. So we have this. So therefore, the equation of motion is okay. What about the initial condition? Also, u hat of t naught equal to, well, e to the power of 1 over ih bar t naught minus t naught h hat. This is a 0 here. So overall, we have the 0 operator up here, and then e to the power, the operator that has all matrix elements 0 is 1. It's the identity operator. This is the identity operator. So here, we defined that e to the power of 0 times operator is equal to the identity operator. Just like e to the power of the number 0 is 1, e to the power of the operator 0 is the identity operator. This is a definition. Whether it is a good or bad definition depends on what the consequences are. And remember this calculation in blue here? We needed, at this point, that the n equals 0 term is going away, because we had a constant here as the n equals 0 term. That's fine if we define this, still true. And we needed that the lowest order term, the n equal 1 term, becomes the m equals 0 term. So we needed that the m equals 0 term, which is a to the power m, in our case it's going to be h hat to the power m, is going to be h hat to the power 0, right? And we need that this is equal to the identity matrix. So here we define this, and generally, h hat to the power 0 is the identity matrix, or any other operator q hat to the power 0 is the identity matrix. At this point, you might wonder, what does this have to do with that? Well, remember how we have that, well, what do we mean by q hat to the power of some number? Let's say q hat to the power of a. What is this? Well, remember, we define something to the power of something else always as e to the power of a, and then the logarithm, in this case, of q hat. This would be the way we do it if q hat was a number. We do it the same way if q hat is an operator. So what do we have in this case here? If we want to calculate q hat to the power 0, well then we have q hat to the power 0 is equal e to the power of 0 times an operator. Okay, now look at this. This is this, and therefore it is the identity operator. So this statement here is the same as these statements. Okay, but what was the point of the exercise that we just did, of the calculation that we just did? We wanted to show that u hat of t naught is indeed the identity matrix. That was the initial condition. So therefore, initial condition, okay. So what we showed is that, in the bigger scheme of things, we showed that in case 1, where the Hamiltonian is constant, where the Hamiltonian does not explicitly at all depend on time, in that case, the time evolution operator is obtained by this exponential. And we proved it by proving that this exponential obeys the equation of motion and the initial condition. So that's as far as we got now. And an important conclusion here is this. If we can find the eigenbasis of the Hamiltonian, then the Hamiltonian is diagonal in that eigenbasis, and exponentiation is going to be trivial. And therefore, we can get the time evolution trivially then. Let me spell this out. So, assume we know the eigenbasis of the Hamiltonian. So we have that the Hamiltonian acting on one of its eigenvectors gives us the eigenvalue times the eigenvector. Well then, what can we conclude? Then from u hat of t equal to e to the power of 1 over I h bar t minus t naught h hat, which is what we just proved, from this fact, it follows that if we apply this equation, the left-hand side and the right-hand side, to an eigenvector of the Hamiltonian, then we obtain that u hat of t acting on an eigenvector equal to e1 over I h bar t minus t naught Hamiltonian acting on the eigenvector. Now we use that if we take the Hamiltonian to some high power, and act with it on an eigenvector, we get the eigenvalue. Oh, that shouldn't be the same. Let's say m. We get the eigenvalue to the m's power. Right? I mean, it's obvious, right? If we apply h hat once on the eigenvector, we get the eigenvalue once. If we apply it 5 times, we get the eigenvalue 5 times. So you get the eigenvalue to the 5th power. So we can use this now. Remember, we're going to use this notation, but we should always keep in mind that what it means is that we have here a power series. And that power series is a power series in h hat. So it contains arbitrarily high powers of h hat. But every occurrence of h hat can be replaced by the eigenvalue, En here, if we let this thing act on an eigenvector. So what we obtain is that u hat of t En equal to E1 over I h bar t minus t naught, and then, well, it's simply En acting on En. So these are complex numbers. These are the eigenvalues of u hat of t. So we have, and therefore we have that if we apply Em u hat of t En, so if you want to know what are the matrix elements of the time evolution operator in the eigenbasis of the Hamiltonian, then we obtain that this is E1 over IH bar t minus t naught En, and then it's En. Well, actually, this is easy, of course. So we can write here simply delta NM, because we know that this is what this is. So therefore, in the basis in which h hat is diagonal, also u hat of t is diagonal. So what we have is that in its eigenbasis, we have that, you know, En is this matrix where we have E1, E2, NM. So the mnth matrix element, maybe I should put an M here and an N there. If this is the Hamiltonian in its eigenbasis, then what the matrix elements of the time evolution operator are is this. It is given by e to the power of 1 over IH bar t minus t naught, and then E1, and then E1 over IH bar. I don't know why the software did this. Over IH, I don't know. Over IH bar, t minus t naught, E2, and so on the diagonal, and zeros on the off diagonal. So the time evolution operator and the Hamiltonian are, in this case, diagonal in the same basis. And you know, if we exponentiate a diagonal matrix, then it's the same as exponentiating its diagonal matrix elements, just by the way that powers of matrices work. It's always matrix element by matrix element on the diagonal. They are just multiplying each other individually without getting mixed. So what we see is that if we have a Hamiltonian that's time independent, then it is super useful to find its eigenbases. Because once we have the eigenbases, we have solved the dynamics. We have solved the problem entirely. That is why previously in the course, we spent quite some time on diagonalizing the Hamiltonian of the harmonic oscillator, diagonalizing X, diagonalizing P, because the techniques that we encountered there are pretty universal. That's usually what we need to do in order to diagonalize a Hamiltonian too. And to diagonalize an operator, if it's the Hamiltonian, is equivalent to solving the dynamical problem of the quantum mechanical system entirely. So diagonalization is equivalent to solving the problem when the Hamiltonian is time independent. Now, what if the Hamiltonian is not time dependent? Not time independent. So this is now case 2. Case 2, h hat of t is time dependent. An example. Example would be an electron in the background of some electromagnetic fields. 2m, and then we have here p vector hat squared plus e over c, e being the electric charge, c being the speed of light, and then a vector of x and t, the whole thing squared minus e phi of x hat and t. Here, this is the electric potential, and this is the magnetic potential. And they're both just, we are here assuming that the electric and the magnetic fields are classical fields, but they can still depend on position and momentum. And so they can depend here on these operators. And we can choose these dependencies in principle any which way we want, because we can expose our electron to a time-dependent electric and a time-dependent magnetic field. For example, we could take an electron which is orbiting a proton. So we would have some Hamiltonian that is just describing, the free particle p squared over 2m plus the Coulomb potential plus this stuff. This would be an electron then that is exposed to the attractive force from a proton, so it forms a hydrogen atom, but this hydrogen atom might be placed in a magnetic field and or an electric field. And if we do that, then the hydrogen atom will be deformed because of it. The hydrogen atom will be overall neutral, for example, but because there's an electric field, it will mess with the electron differently than with the proton. It will pull the proton in the opposite direction in the electron, and therefore the hydrogen atom will be slightly deformed. Its energy levels will be deformed. And if you do that in a time-dependent way, if you change the electric field in which the hydrogen atom is placed, then you have a time-dependent Hamiltonian. And that means that the spectrum of the Hamiltonian will be time-dependent. It also means that the eigenvectors of the Hamiltonian will be time-dependent. This is the case that we are considering here. The case of a Hamiltonian whose spectrum can be time-dependent, whose eigenvectors can be time-dependent. In fact, the Hamiltonian at one time may not commute with the Hamiltonian at another time because it's a different operator. And that is exactly the non-triviality that arises here when the Hamiltonian is time-dependent. The non-triviality being that the Hamiltonian at one time may not commute with the Hamiltonian at a later time. So then what? Then what is u hat of t then? Well, let's make a guess and then see if it works or not. So we guess that maybe u hat of t is equal to, let's put a question mark over it, e to the power of 1 over I h bar, and then integral from t naught to t of h hat of t prime dt prime. Why is that a good guess? Well, it reduces to the usual case when, to the previous case when the Hamiltonian is not time dependent. So check. If h hat is constant, then we have that this is equal to e to the power of 1 over I h bar integral t naught to t of h hat dt prime, but that's simply e to the power of 1 over I h bar h hat and then t minus t naught, right? So this is what we had before. But can it be correct? Let's see. This is a non-trivial business here because the equation of motion involves a derivative. And then the Hamiltonian here comes up in different, at different times, and it may not commute at different times with itself. So the next check is this. So the first check, it passed. It reduces to case 1 when it should reduce to case 1. But let's check this now. What is IH bar d by dt of u hat of t? Is it, as it should be, u hat of t, h hat of t? Let's see. We have IH bar d by dt of the proposed u hat of t, which is this thing here, of e to the power 1 over IH bar integral t naught to t h hat of t prime dt prime. What is that? Well, we have to spell out what it is. It's IH bar d by dt of the sum n equals 0 to infinity of 1 over IH bar to the power n, and then that entire integral here to the power n, t naught to t, h hat of t prime dt prime to the power of n, and then 1 over n factorial. At this point, you may get a hint that solving a quantum mechanical problem can be hard because you have to take these infinite powers of integrals over non-commuting operators in order to solve a generic quantum theoretical problem. By the way, the calculation we're doing today is the exact same calculation for quantum fields. We are not really assuming here anything particular about the x hat or p hat. This is just generic quantum theory as applied to whatever, even in cosmology or wherever these time evolution operators come up. All right, so it's this, and we have to differentiate that. So now we have to differentiate all of this, and this is the power of n, right? Okay, so we have to differentiate this series with respect to time. There's no time dependence here, no time dependence there, but there's a time dependence of the integral. And so what do we get? We obtain that this is equal to sum over n equal 1 to infinity. We lost the 0 term because some operator to the power of 0 is some constant operator. In fact, it's the identity. So if we differentiate with respect to t, it's going to be 0. So we're losing the 0 order term. And then we have an IH bar here from here in front. And I'm putting here an IH bar. I'm taking that away from this nth power. And then I'm left with 1 over IH bar to the power n minus 1. And then, and then we have a 1 over n factorial. And then we have, by the product rule, to differentiate this thing. But you have to be very careful here. Let me show you why. There's something non-trivial happening, and you may not have seen this kind of derivative before. So let's write this as this bracket times n minus 1 times that bracket. So we differentiate the first term here. So what's the derivative of this with respect to t? By the fundamental theorem of calculus, this is h hat of t times the stuff that we didn't differentiate, and that's t naught to t, and then h hat of t prime dt prime to the power of n minus 1. And it's important that this term is to the left and that's to the right, because we have differentiated the first of those n factors with respect to t, and we got that. And this is generally not commuting with that. See, because this is a time-dependent operator. This operator, that whole thing here, has no reason to commute with this one. So generally it doesn't. That's only the first term. Now, the second term here is obtained by leaving the first of those n factors the same. So we integrate from t naught to t, and then we have here h hat of t prime dt prime. And then we differentiate the second factor, and that gives us an h hat of t. And then we have n minus 2 factors left over. So integral from t naught to t, h hat of t prime dt prime to the power of n minus 2 plus plus the case where we leave the first 2 factors undifferentiated, we differentiate the third factor, and then we get the remaining terms. So dot, 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 plus at the end, we have the integral from t naught to t, h hat of t prime dt prime, n minus 1 times, and the nth factor is the one that we differentiate, and we get an h hat of t from that. And then we close the big bracket. Now, if this integral was an operator, if it is an operator that commutes with h hat of t, then we simply have n times the same term here. But if it doesn't commute with h hat, then we have, in principle, n different terms that we are summing up. Okay, so but what do we need? Well, we would need here that this commutes with h hat, because if it does, then all of the terms, all of those n terms could be written as this term, right? Where we simply have all of the n minus 1 integrals to the left and the h hat to the right. And then we would have n times this term. And this factor n cancels one of those n's in this n factorial here, so that we get 1 over n minus 1 factorial, 1 over IH bar n minus 1, and we get this thing to the power n minus 1 and the h hat, and we would have, in this case, we would have what we should have, namely, we would have the u hat of t times the h hat to the right? Times the h hat to the right. But we don't get this because we have the h hat here in the middle, and generically we have to assume it doesn't commute with this integral. So that's the problem with the time evolution of a quantum mechanical system. Just write it up, trouble, because we have that the commutator between t naught and t, h hat of t prime dt prime with h hat of t not equal 0 in general. So what to do about this? Well, the solution is to introduce what is called the time ordering operator. Solution, introduce time ordering operator. And it's usually denoted by a capital tau. And capital tau is defined to do the following. It acts on products of the Hamiltonian. If we take the Hamiltonian at time t1, multiply it with the Hamiltonian at time t2, until Hamiltonian at time tn, then this is, by definition, this is the Hamiltonian at time t1 tilde. I'll explain in a sec what the business is with this, t2 tilde, dot, 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 until h hat of tn tilde. Now, what is the difference between the t's and the t tildes? Here, we have that t1, t2, t3 are arbitrary, non-ordered times. So this could be 5 seconds, 2 seconds, 27 seconds, 500 seconds, 0.3 seconds, etc. These are points in time, but they are generically not necessarily ordered. And the t tilde I are the same times, but ordered. So we have that t tilde 1 smaller equal to t tilde 2, smaller equal to t tilde 3, smaller equal to dot, 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 smaller equal to t tilde n. So what this is saying is that if you take products of the Hamiltonian at different times and you apply the time ordering operator on that, then you get again a product of these same Hamiltonians at the same times. But it's ordered now such that the Hamiltonians at earlier times are to the left of the Hamiltonians at later times. Now, why would that come up? Well, remember that this was our ansatz here. This was our idea for what the time evolution operator could be, right? So we said maybe the time evolution operator is this one. And then we found there's a problem. There's a problem because when we write this out as a power series, the Hamiltonian can occur anywhere between those integrals where it doesn't commute with the integrated thing, right? Or look at it differently. If we write it as a power series, as we do, as we do here, as a power series, let me just spell it out. Okay, so if we wanted to spell out this thing here, if you want to spell out what this is, what is it? Well, it's the sum n equals 0 to infinity, and then 1 over IH bar to the power n, 1 over n factorial. And then we have all those many integrals, namely n of them. And then we have the h hat, etc., dt prime, dt double prime, etc., n of those. Right? That's what we get. We get products of Hamiltonians at different times, and all those times run from t naught to t. So therefore, we have here Hamiltonians, products of Hamiltonians at different times. And what we need is that when we differentiate with respect to t, the Hamiltonian that we get by the fundamental theorem of calculus, the unintegrated Hamiltonian, has to be to the rightmost, because we want to fulfill this equation of motion. When we differentiate the unitary time evolution operator, the Hamiltonian that we get from the differentiation of the exponential must end up to the right of the exponential. So that's the late-most time. Hamiltonian at the most late time must end up on the right. That's why the time evolution operator is doing this. If we have Hamiltonians with arbitrary time ordering, then we reorder them using the time ordering operator such that the Hamiltonian with the latest time is to the very right. Okay, so proposition one can prove, but I won't prove it here, that u hat of t is equal to time evolution operator, a time ordering operator acting on e to the power 1 over I h bar integral t naught to t of h hat of t prime dt prime. And just to spell out what that really is, because this is just a notation, what is it really when we want to work it out? Well, this is then the sum of a series n equals 0 to infinity, and you're now seeing in real life happening why quantum mechanics is hard, or why quantum theory is hard, and what it is we do when we calculate in particle physics the scattering processes between protons and electrons and so on. What goes into it? Let me show you. So if we spell out what this is, this time ordering operator is going to apply to the powers in h that arise in this from the multiple integrals that we get. So what it's going to be is this. It's 1 over I h bar to the power n, 1 over n factorial, and then it's all those integrals, namely n of those, dot, 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 integral. Each one from t naught to t, t naught to t, t naught to t. There are n of them. And then we have here the time ordering operator. And then we have the Hamiltonian of, let's call it T1, h hat, and h hat of T2 until h hat of Tn. And this is what the time ordering operator acts on. It will reorder them such that the Hamiltonian with the latest time is to the rightmost. And then we have dt1, dt2, dot, dot, dtn. Right, so this is what it is by definition. So when we have time-dependent Hamiltonians, then that's what we are faced with. When you have time-dependent Hamiltonians, it obviously can't suffice to just diagonalize the Hamiltonian once, because it's changing. So its spectrum can change, its eigenvectors can change. Therefore, it's always desirable to have a Hamiltonian that's time-independent, but sometimes it's, of course, not avoidable. For example, we may want to steer a quantum computer's operation. Then we want to be able to, from the outside, influence the dynamics of our quantum system. And that means we are introducing parameters from the outside, often, in fact, electric or magnetic fields. And then they will mess with the dynamics, and this is, in principle, how we have to calculate all those things. Now, for quantum computers, that's not so hard yet. But if we do this for more complicated systems, such as complicated interactions between elementary particles, especially if it's lots of them. And if we calculate to higher order and perturbation theory, so if you go to higher exponentials there, higher powers in here, in this series expansion, then this can get really complicated. And there is a whole business of how to evaluate these higher powers in these integrals of higher powers of time-ordered products of Hamiltonians. You can look this up under the keyword of Wick's theorem. So this is what's going on at the heart of many calculations in quantum theory. But to complete the proposition says that this so defined time evolution operator obeys the equations of motion. So it obeys that IH bar d by dt of u hat of t equal to u hat of t h hat of t with all of its glorious time dependence and the initial condition u hat of t naught equal to the identity. So it's the solution, even though it might be hard to obtain. Now to conclude, let's collect a few nice properties of the time evolution operator. Properties of u hat of t. Now, first property is that time evolution operator for every point in time t is unitary. So, i.e., we have that u hat dagger of t is equal to u hat inverse of t. Check e.g. for case 1, i.e. to say, this is to say when the Hamiltonian is constant in time, then we have that u hat of t is equal to e to the power of 1 over ih bar t minus t naught h hat. And then we have that u hat of t dagger is e to the power of minus 1 over ih bar t minus t naught h hat. And this is indeed the inverse of u hat equal to u hat inverse of t. And how do you see that this must be the case? Remember that the unitary is diagonal in the same basis as the Hamiltonian is. And that means that the eigenvalues of the unitary are given by e to the power of 1 over ih bar t minus t naught and then en. Remember we had that earlier in this lecture. So the eigenvalues are phases, are complex numbers on the unit circle in the complex plane. And they have, of course, the property that when you take their complex conjugate, they are their inverse. So because h can be diagonalized, u can be diagonalized. And therefore, by the same reason that e to the power of minus an exponential is the inverse of that exponential, we still have that this is the case here. Okay, so we have that the unitary is, that the time evolution operator is unitary. This can also be shown for the case 2, when we have the time ordering operator involved. It's still true. It's just a bit more complicated to see. Another property of u hat of t, the time evolution operator, is that it respects or conserves hermiticity. So assume that f hat of t naught dagger is f hat of t naught. So we have the hermeticity condition obeyed at the initial time. Now, we know that u hat of t is propagating it forward in time. So then we have that f hat of t is equal to u hat dagger of t, f hat of t naught, u hat of t. Remember, this is what the time evolution operator does. That's its job. It takes an observable at some early time and then tells you what the observable is at a late time. So then this obeys that f hat of t dagger is equal to, well, let's see, we have to take the dagger of that whole thing here. When we take the dagger of that, then the sequence in which the operators occur is flipped. So we have to take u hat, move it over to the left, and dagger it. So we get u hat dagger of t. And then that term stays in the middle, f hat dagger of t naught, but f hat dagger of t naught is f hat of t naught, right? And then this operator moves to the very right and is Hamiltonian conjugated. But if you have Hamiltonian conjugated twice, you get back the original operator, so you get u hat of t. And therefore, we have that this is f hat of t by definition of it. So therefore, hermeticity is also respected. And third, u hat of t respects the, well, not just the canonical commutation relations, respects all commutation relations. So this means in particular that if you have that x of t naught and p of t naught obey some commutation relation, it could be that the commutator is just IH bar, or it could be that it's the case where gravity somehow intervenes and the commutator between x and p is more complicated on the right-hand side. No matter what the commutation relations are at the initial time, the time evolution operator, which does this job, time evolution operator, which does this job, respects the commutation relations. The same commutation relations that two operators obey at the early time, they will also obey at the late time. And this will be an exercise, C exercise, to prove that this is the case. Okay, so this is as far as we got today.